Bad news, everybody. Turns out everything you've learned up till now is only applicable 50% of the time. Unbeknownst to us, everything I've been teaching you about the right-hand rule is only true if the system is on and you're coming in to turn it off. Meet Lenz's law, what happens the other 50% of the time, and the reversed right-hand rule. Once we have the two principles taken down, it won't be that bad. Let's start with Faraday's law that we finished learning about in the last lesson. The EMF, the voltage generated by your generator, depends on number of coils, that's constant. The area of the coil, that's constant. The speed at which you're turning, let's say that's constant. Crank it up, and it varies sinusoidally. Now, we were assuming when you had a generator that your generator was hooked up to a permanent magnet. Who uses permanent magnets? It would be much more convenient for it to be hooked up to an electromagnet, especially since we've been saying from the start that you wanted to increase the magnetic field. Well, you're only going to be able to do that if you have an electromagnet. If you look up Ampere's law and the calculus behind it, you'll find that B, the magnetic field around a wire carrying a current of I, such that you are over here somewhere, a distance r from the wire, or, to be fair, not just there, that anywhere else along that equal potential, the magnetic field will be directly proportional to the magnetic permeability of free space, and how inversely proportional to how far away you are, and directly proportional, of course, to the strength of the current. So if you want a stronger magnetic field, run a stronger current through your wire. We said in Faraday's law that the EMF is proportional to the change in magnetic flux over time. Well, if your magnetic field is changing over time because you're increasing the current, the result is going to be directly proportional to, that's what this little sign means, the change in the current. If you don't change the current, the magnetic field is going to be constant. It's not going to show up in anybody's derivative. But if you do change the current, then this simplistic NAB omega sine omega t that we checked off last time is no longer going to be the full story. This B is going to need to go back in the derivative, and you're going to need to look at the change in the magnetic field, and that Lenz's law. There is your collection of constants out front. We're going to call it L. L stands for the inductance of your inductor. Remember those little inductors, those coils of wire that you took notes on way back when we were doing circuit diagrams and circuit notation? Now we're ready to use it. The inductance of the coil of wire will depend on the number of turns in the coil, the cross-sectional area of the coil. All these variables will go in there for L. If you're lucky, L is written on the package when you open the equipment. The EMF that little inductor will generate will be directly proportional to the inductance, how much it resists change, and directly proportional to the size of the change, only negative. Those two principles alone will take us the rest of this lecture. Think about it. The more you have a change, the more the system resists the change. That's what the negative means. This negative is electromagnetic inertia. All systems resist change. The system that is best set up to resist change most successfully is a coil of wire with many turns in a large area. The more it changes, the more the system resists the change. Let's think about this conceptually. It turns from off to on. This is a huge change. A huge change in electric field generates a change in magnetic field. There wasn't a magnetic field before because there wasn't a current before. There was nothing. But that magnetic field, by virtue of being called into existence over a virtually instantaneous period of time when you turn the current on, that was a change. It was a change from non-existent to existent. And that change in magnetic field also creates a change in electric field. So we're back where we were before we started. The change in electric field creates a change in magnetic field, which creates a change in electric field. And Lenz's law explains this isn't a contradiction in terms. This is civil disobedience. The change in electric field, the new one, is there to resist the original change. The electric field changes, causes a surge in the magnetic field. The magnetic field is there to push the electric field right back where it started. Or if you want to do this with magnet, in magnetic field, south going in, will generate a surge in the electric field, a change in the current in this coil, and that change in the current will generate a magnetic field to push south right back out the way it came and say, no thank you, we were happy enough with the way things were before, we don't want change. Systems resist change. If you bring a magnetic field into the system will try to push it right back out again. However, if the magnetic field was in the system to begin with, and you try to pull it out, again, you'll get a change in electric field, you'll get a surge of current. That surge of current will try to maintain the magnetic field and say, hey, I was happy with a north pole right over here and a south pole right over there. I want to maintain that field. Bring that magnet back. I miss it. I will try to keep up its magnetic field for as long as I can, even when the magnet has gone away. Is electromagnetic induction. And it's what most people talk about when they're using the word induction. Change in electric field creates a change in magnetic field that is there to resist the change and return the system to the state that it was before. This can be the right-hand rule to maintain, or the reverse right-hand rule to bring us back to a state of zero. Time you look at a problem with an inductor, a change of any kind, you want to look to resist that change, to maintain the status quo. That's why there are two totally separate cases for every circuit, for every change. Case of the circuit that is off, where the change is switching on, and a completely different case where the system is on and has been on for a significant amount of time, and you want to switch it off. This is the one we've learned about already. If the system is already on and you switch it off, that system resists change. The inductor, the coil of wire, will try to maintain the magnetic field. It will try to stay on. This is the right-hand rule as we've all learned it. The current was coming out of the screen this way, flowing counterclockwise through your inductor. It will make a magnetic field, again, coming out of the screen, going this way, to make a magnetic field right through the center of that coil. And it will try to maintain that field for as long as the inductance of the system allows it. We'll do the graphs in a minute. We'll see how many microseconds it's likely to be. However, if the system was off and has been off for a long time, and you're trying to switch it on, then the system is going to oppose the new magnetic field. It's going to say, no, get out. And the magnetic field of the coil is going to work to surge that magnet out of the way, or the electric field around the magnet is going to surge to make that current go off. And this is going to be the reverse right-hand rule. what you do is the same thing as before. Here's the coil. Here is the direction that the current is trying to go. Now, you sit there and you do the exact opposite. If the current is trying to come out of your screen going this way, with the magnetic field going that way toward the right, then know for a fact that the coil will have a surge of current making an enormous magnetic field. How enormous? Well, just for a moment, the same size as the one you're bringing in, going to the left. Now, do the right-hand rule on a current that's going the other way, and see that the current through this coil will actually flow clockwise, opposing the direction. Over time, this process dies down. Why? Because if the system is 100% successful in resisting the change, if the inductance is so big that L di dt pushing an equivalent EMF, this is called a back EMF because it's pushing backwards against the voltage of whatever battery you have. If L di dt, you've got a huge change and a huge inductance, is equal to the 9 volts of battery voltage in the system you've just connected and turned on, then 9 volts of battery voltage minus 9 volts of back EMF is going to be 0. You don't get a current if you have 0 volts, so the system was successful in resisting change. No current, no problem, no change, no change, no change in current, no change in current, no magnetic field, no magnetic field, no back EMF. Well, it looks like the 9 volts can continue unimpeded now. Something that depends on the change of a change. Smells like calculus to me. Let's model the solution and see what it looks like. Lenz's law and the reverse right-hand rule in your notes. If you've made it this far, you are well prepared for any pre-collegiate standardized test there is. This is the one area where more of my students find themselves having to cram and find themselves getting the exact opposite answer of what the cram book says regarding electromagnetism, knowing the difference between a circuit that's on when you're switching off and a circuit that's off when you're switching on. Work practice problems in your study guide and your textbook, making sure you're using the right-hand rule where and when it was meant to be used. Lenz's law as a differential equation. We will clear up the differences in our notation. Many textbooks use curly E for all kinds of voltage, but given that it's not actually a force, I don't want to support their enterprise. We've always called voltage V, as in VB, the battery voltage, and that's because last chapter when we did circuits, just about everything was DC because we didn't have a reason to use AC. E, curly E, is the back EMF. You know what? Even batteries have a certain amount of internal resistance. All devices have inductance. All devices have a certain amount of back EMF. And curly E is usually used for the one that's in the way, the one that's restricting the flow, the one that you don't want. Frankly, generators work the same way if you don't mind cranking this way with a magnetic field as you turn on for an effect that goes that way. Generating voltage, you want to use curly E for a generator, be my guest. The point is, now that we have this, we remember that V equals IR. And if you're looking at the inductance of an inductor in a circuit, you can see the first order differential equation right here. People who've been sneaking looks at the AP videos elsewhere on this channel know that the first step in a differential equation is to get the derivative by itself. So move this minus L to the other side, pause, press play to check your work. Also nice to put the derivative on the left-hand side where we can see the calculus coming from 100 miles away and take evasive action. We have that all-important negative sign we've been taking from here. There's the function on one side, there's the derivative on the other, and we've got an L over R set of constants that we can keep out front. From here, We can do this the calculus way. Look at the differential equation, recognize the solution from 99 miles away and write down the answer, or the pre-calculus way, which is to model the system as a system, make a graph, and fit the equation to the graph. Let's try them both. Start with the on case. For one thing, it looks easier because it's every rule we've ever learned. We know if we're looking at the current over time, what the initial value is and what the final value is, and we ought to be able to fit a graph in between without too much trouble. If the system was on, there is an initial value of V over R. V, the battery voltage minding its own business, not caring about the inductor because there isn't any change, and R, the resistance of the circuit. We know I equals V over R. That's Ohm's law. There's our initial value, V over R. We also know what the final value is going to be. Sooner or later, this final value is going to be 0. Now let's look at the slope. Slope is the rate of change. In pre-calculus, this says delta I over delta t. That should be the slope of the I over t graph. In the end, the system is off, and it's been off for a while, so it's going to have a very low slope. In the beginning, a switch has very suddenly been flipped. That's an enormous change. It's going to have a very high slope. Now let's connect the dots. What goes from a high slope to a low slope, like this. Anybody recognize that
Exponential decay
shape? Sure. So here's our starting value, and it exponentially decays over time. The only thing we really need to bake brownies for the calculus class for is that rate over here of L over R. Calculus class, check the pre-calculus math, take the first derivative of that I as above. You will get V over R. There's a constant, that's not going to change anything. Chain rule, negative L over R, and the rest of the function back as it was before, minding its own business, which is exactly what our differential equation said was going to happen. We should get the original function times an additional negative L over R. That's how we know we're right. Question: what function has a first derivative of itself, only negative, and with some constant up front? Exponential decay. Here it is, the solution for the problem of a circuit that's on and switching off. If your circuit has an inductor, the current will exponentially decay over time from an initial value of V over R to a final value of 0. Switch on. We've got our initial value. Circuit is off. I equals 0 at the beginning. This time it's our final value. That's V over R. And it's going to be V over R for quite some time. We call it the circuit being on. For quite a while, it's going to be V over R. And look, this looks to me very much like an asymptote. We're going to have the same slope issue we had before. We're going to have a very high slope at the beginning because there's a very sudden change in the current, and we're going to have a very low slope at the end because the current has been on for some time. High slope, low slope. Connect the dots. We know what we're looking for this time, so the curve is going to be a lot more smooth. I'd love to say this is exponential growth, but it's just not true. Take a look. This is exponential decay, flipped upside down over the x-axis and shifted up by a certain value to get that asymptote, the one over here, away from the x-axis and up to, bless my soul, a final value of V over R. This is graphical transformations, the same as any Algebra 2 student does. List the graphical transformations and see what you get. Press play to check your work. We start with our exponential decay. That's PERT, and we're going to do with PERT. First, notice we have to do this chronologically. we have to flip upside down. That's a negative leading coefficient. And then we have to shift up. How much? Well, we can see by V over R. You'll pardon me for being a canny guesser and guessing the rate is going to be L over R just like it was before. And we have to shift up by a plus C, or in this case, plus V over R. Now, we've got two, they're called boundary value conditions. They're the opposite of the boundary value conditions that we had before. Before we had to start at V over R. That was easy because e to the negative t equals 0. That meant this is 1. 1 times V over R is 1. And we had to decrease to a final asymptote of 0. Now, when we plug in t here, this is going to be 0. E to the negative 0 is 1. That means A plus V over R has to be 0. Clearly, A equals negative V over R. Otherwise, we're not going to go through the 0, 0 point. So, with a little bit of surgery here, we can finalize this. There we are. And while we're at it, we might as well pull out a leading coefficient of V over R because it appears in every term. And once we've done that, oh God, I don't want to lead with a minus sign. Nobody leads with a minus sign. Can we lead with a positive one, please? Oh, good. 1 minus, and here is our exponential decay function, as ever was, e to the negative L over R times t. Calculus bunnies, take the derivative of this. You're going to notice that the first term drops out. Derivative of a constant is 0. We have negative V over R e to the negative L over RT. Take the derivative of that. You'll multiply by negative L over R. You will get negative L over R times the original. You're going to have to do 2 steps of algebra to see what happens to this plus V over R here. Give yourself a smiley face when it works out despite everything. And you find that the pre-calcers had it right. This is exponential decay flipped upside down and shifted up. It's not exponential growth, it's reverse exponential decay, and that's what happens when you're switching something on. It gradually increases to a final value. What determines whether this is a very steep drop off or this is a very gentle increase? L does. The strength of the inductor. It's also inversely proportional to the size of a resistor. A resistor resists. That's where the internal resistance of the battery comes in.